Thank you very much, and thank you for the invitation to talk here at this workshop. I'm sorry I can't be there in person, but it's great to be able to do it remotely anyway. So I'm going to tell you just a bit about another set of tools called Black Hole Perturbation Toolkit, which I've been developing with collaborators. And as the name says, this is really kind of focusing on black hole perturbation theory as its main goal, although you might find that some of the tools are also useful for other things, including, for example, some things you might do in numerical relativity. Okay, so before I get into the toolkit, it's worth maybe just giving a little bit of motivation. Well, first of all, even before we motivate the toolkit itself, why do we care about black hole perturbation theory? Well, one of the biggest drivers at the moment is that we are pretty hopeful that in the next 10 to 15 years, the LISA mission will launch and we'll start taking data and we'll start observing gravitational waves from a whole load of new sources that are in a very different frequency band than what LIGO would see. So this is just a kind of a representative picture of the sensitivity range of LISA. And the important thing to look at here is along the x-axis, you have the frequency range. So it's 10 to the minus 5 down to 1-ish hertz. LIGO would sit over more or less to the right of this in the kind of 10 to the 0 hertz-ish range. And the other thing to look at this is that you have a whole load of extra, well, you've got this curve here, which is the kind of the noise floor in LISA. So anything above this, LISA will be able to see. And you see a whole lot of sources in here. Some of these really big, loud ones are sources that are very similar to what LIGO sees at the moment. These are massive black hole binaries. So two very, very large black holes merging. They'll have a lower frequency, but very high amplitude in the signal compared to existing LISA sources. And these ones, there's an awful lot of hope that existing numerical relativity methods, like has been talked about this week, like the Einstein toolkit is able to do, and also like GR-Chombo can do, and others, there's a good hope that they'll be able to produce waveform models for these types of signals reasonably well. Although there are extra challenges, probably they may be slightly different in terms of mass ratios or eccentricities and things like that. But then if you look a little bit lower down, there are these dark red streaks, and these represent harmonics of what are called extreme mass ratio inspirals. These are binary black hole systems where you have two black holes, but now they're not the same size anymore, but one is much, much larger than the other. Perhaps 1,000,000 times or certainly 10,000 times larger. The bigger one is than the smaller one. And these are really great candidates for LISA because although they live down here, lower down, they're not as loud as the big ones, they carry an awful lot of information about the space-time of the big black hole. And one of the stated goals of the LISA mission is to both detect and estimate parameters for these extreme mass ratio inspirals. Now, when you actually think about what that means, well, that means we're going to have to build a model for these systems. We're going to have to figure out what the waveforms for these things are so that we can do match filtering. And once we've done match filtering, we can detect first and then extract parameters about the system. Now that sounds like something we do all the time for LIGO these days, but there's a big problem here. And the big problem is that these extreme mass ratio inspirals are very different than comparable mass systems. They've got they're two very different length scales. So that's certainly going to be a problem just if you think in terms of resolution. And similarly, there are two time scales. There's an orbital time scale and there's an inspiral time scale, which are no longer comparable to each other. So that's another problem for kind of typical numerical relativity simulations. And if you do the numbers, you quickly work out that you need basically an inordinate amount of computer time just to do any sort of a simulation with existing full numerical relativity techniques. So that's where black hole perturbation theory comes in. We use the thing that seems to be a problem, the fact that you've got this two different length scales, this mass ratio, to turn it into an advantage and use it as a small parameter to reformulate the problem using what's called black hole perturbation theory. So black hole perturbation theory basically says that you've got these two black holes here, the big guy and the small guy, and they might be spinning and the spins might not be aligned, and you have some gravitational waves coming off. We want to build a model for this system, and it's going to be extremely hard to solve the full Einstein equations for the metric G alpha beta. But what we can do is we can think about this metric as having a formal expansion in powers of this perturbation parameter epsilon, which if we choose epsilon to be the ratio of the mass of the small black hole to the big one, will be a small parameter. Then we can try and write down equations for this G bar, this background solution of the Einstein equations, and this H1 and H2. And we could keep going as long as we have stamina for. Now, what actually we need to do to produce a waveform is not just solve Einstein's equation, but we actually have to work out what the gravitational wave signal is. And if you do that, you can think of the signal as being a wave. It has an amplitude and a phase. And if you do the analysis to look at how the phase depends on this expansion in powers of the mass ratio, you find that the leading order piece involves just this H1, and it goes like 1 over the mass ratio. So that's going to be a very large number for a very small mass ratio system. You then have a correction at order epsilon to the 0, so order 1, so 1 radian in phase, and that has contributions that involve both H1 and H2. And then you have higher order and mass ratio things. These are going to be small when epsilon is small. So we can immediately read off this that we're going to have to do perturbation theory, and we're going to have to compute H1 and H2. And as soon as you do that, you make one key observation, which is just writing a code for doing, for example, generic Kerr orbits using the Teukolsky equation to solve for this H1 dissipative on its own is already beyond the scope of what you would reasonably ask a PhD student to do in their project. And any hope of going all the way to the end here is really a big challenge. So how are we going to deal with that? Well, what we can do is we can kind of take some inspiration from the numerical relativity community. They faced very similar challenges back in the early 2000s. So back in the 90s and the early 2000s, there were an awful lot of people working very hard in numerical relativity, with making some progress, but no one quite managed to crack it. Then around 2005, there was the great breakthrough, where finally the first simulations were run through the merger, and really it was the dawn of the era of kind of numerical relativity as a way of really producing waveforms for binary systems. If you then think about the timeline starting from that 2005 detection onwards, or the breakthrough in 2005, about 10 years later was when LIGO announced their great results that they observed these things. And in those intervening 10 years, there was an awful lot of work. 2005 wasn't the end of the story. An awful lot of further development was needed to get the models ready. And it was only really just in time for the LIGO detection that the waveforms were really kind of robust. And one of the key ways that this was achieved was that there were successful software collaborations like the Einstein Toolkit that really made it possible to produce these simulations and waveforms robustly. So we're now at a new era where LISA is about 10 years away. We have just last year produced the first ever post-adiabatic waveform. That's a waveform where we've included that order 1 radian phase piece. So we've computed H1 and H2. LISA's, as I said, 12 to 14 to 15, whatever years away. We're going to need a lot of work to do to go from these kind of proof of principle things to models that are really ready for the sort of data analysis LISA is going to do. And the only realistic way we can do this is if we're going to mimic what NR did 20 years ago and build some successful collaborations so that we're not reinventing the wheel every time. And that was really where the idea for the Black Hole Perturbation Theory Toolkit came from. It came from a series of conferences, the Capra conference, where there were a lot of people working on this problem individually, and not a whole lot of sharing of results, and in particular, not a whole lot of sharing of code. So out of this, a number of us came together and decided, well, we should fix this and we should start to put together useful tools for the community to use and to build on. And that's where this statement of purpose for the Black Hole Perturbation Toolkit really came out of. So just reading this out for you, our goal is for less researcher time to be spent writing code and debugging, and more time spent actually using that code to do physics. At the time, there were multiple scattered Black Hole Perturbation Theory codes. They were developed by a wide range of individuals or groups over a number of decades, but they were private. and they kind of stuck to the one person, and if that person lost interest, they kind of died. So the aim of the Black Hole Perturbation Toolkit is to bring together some of the core elements of those codes into a toolkit that can be used for all. And the second goal, as well as providing the code, is that we also want to provide easy open access to the data that's produced in many of these calculations. So this effort started out as a joint effort between myself and colleagues at University College Dublin, and also collaborators at the University of North Carolina at Chapel Hill and MIT Kavli Institute. But really, to be fair to everyone, it's been a success because of the involvement of a much wider community of people, both contributing to the toolkit and using it in their own research. So this next slide is something I usually show when I give one of these talks, and it's exciting that I always have to update it each time because we're adding new people. So just taking a census of who uses the code and where. What we have here is a map of the Earth, and you've got the three red ones are the kind of the founding institutions: Dublin, Chapel Hill, and MIT. But then you have a number of users in yellow, and also contributors in blue. And it's been nice to see various parts of the world getting filled in over time, over the last couple of years, as the use of the toolkit has grown. So that's been one really nice measure of how useful it has been to quite a wide community that has kind of got very international usage. The other way we've kept track of this, so you can get an up-to-date version of this plot if you go to this website down here. The other way we keep track of this is by just counting a crude count of the number of citations. Now, we don't yet have a published paper describing the toolkit. So the way we count these citations is just by people who acknowledge the toolkit in the acknowledgements of their paper. We started this count back when the toolkit was founded in 2017 or so. There were none at that point. It's been really exciting to see an initial kind of slow start and then a great takeoff in the number of other science papers which have used the toolkit. And we're now up at 84 papers that have used it as of this year. And also in red here, you've got another measure, which is the number of papers that have cited the toolkit and also contributed some of their code back to the toolkit. So these are two very nice things to see, especially the blue one is a nice steady growth. Perhaps there's been a little bit of a slowdown over the last couple of years in terms of development. I guess we can kind of guess why that is, but we're hoping in this summer and beyond to kind of lift this curve up again. And we're going to do a big push in development. We've got some nice ideas coming up for the summer. Okay, so that's kind of the motivation and what the toolkit is. Later today, my colleague Niels Warburton will give a tutorial on how to use the toolkit. For now, I just maybe want to give you a quick flavor of what's there, what you can use, and what's there and what you can use it for. So in terms of the components of the Black Hole Perturbation Toolkit, well, they're breaks down into two categories. We have code, which is developed in a number of languages. We typically target.
2 years before.
Sorry, was there a question there, or?
It was like for a year and a half or something.
So the code is developed. The toolkit is developed in 3 main languages. So we have a fairly large amount of Mathematica code. That's not necessarily designed for the most blazing fast performance, but it's really designed to be user friendly and easy to kind of do a lot of analysis and some relatively sophisticated calculations as well. We also have some lower level C, C++, and Fortran codes, which are designed for speed above all else. And then we've got some Python as well as that. So we target those 3 languages mainly because the developers, they're the ones that they use. But really, we're happy to include any code as long as it's got high quality, well documented. Doesn't matter about the language. And we're not too prescriptive on the license as long as it's open source. Most of the code released so far has been under either the MIT or the GPL licenses. I mentioned earlier, as well as code, we also try to gather, collect and collate all of the data that's been released over the years. So for example, gravitational wave energy fluxes. In the self-force community, local invariants are a big thing that people compute. Post-Newtonian series are something that you really don't want to ever type in from a paper. So we try to collect them as much as possible in electronic form. And again, in the self-force community, regularization parameters are a big feature. So these all fall into the category of data rather than code. Most of this data that's been provided so far has been for the simplest cases where you have perhaps a circular orbit in the equatorial plane. But we are bringing data online that's kind of more generic, so eccentric orbits, inclined orbits and things like that. Initially, when we started out kind of gathering the data, we particularly used something like Google Drive, but later transitioned to more permanent storage, such as Zenodo, once the data sets are finalized. So drilling down into this a bit now, into the codes first. Well, on the Mathematica side, there are a number of interlinked packages. We've got one for computing the spin-weighted spheroidal harmonics. This is the one that I was talking about, may be also useful for people who do NR because you need spin-weighted spherical harmonics there, and it can do those. We have a nice code for solving geodesic equations in Kerr and computing a lot of the associated quantities. So the video on my first slide was generated using this package. And then we've got codes for solving the perturbation theory equations, either the Teukolsky equation or the Reggie-Wheeler equation. Those are the equations you need to solve to get that H1 and H2 I showed earlier. And then these are actually very tightly linked together. They work together and they rely on each other. We also have two additional codes, one called general relativity tensors, which is a fairly lightweight tensor algebra system for doing tensor algebra and Mathematica, and component calculations in particular. And a second one to compute quasi-normal modes, their frequencies, and so on. So I have a slide on each of these just to kind of give you a flavor of what these codes can do. So for example, the spin-weighted spheroidal harmonics package allows you to do a number of things. It allows you to evaluate the harmonics for a start and their eigenvalues to arbitrary precision, so beyond machine precision if you want, and even analytically in some cases. And that's for both the eigenvalues and for the harmonics. So for example, here on the left, I've got a Mathematica window where I show that you can build up a table of the spin-weighted spheroidal harmonics with S equals -2, L equals 2, M is either -2, -1, 0, 1, or 2. So M goes from -L to L. And gamma is the spheroidicity parameter. That's how much it is different from a spherical harmonic. And then this is now a set of functions which we can plot as a function of theta. And the nice thing here is that it really tries very hard to present a very kind of intuitive interface for people who are used to Mathematica. It just behaves like any other Mathematica function. And in many ways, that's true. For start, it can be numerically evaluated, but also you can do series expansions. So if you want to know the series expansion of these things for small spheroidicity, for example, you just use the series function in Mathematica and you get out this sort of expression down here. And there are also series expansions about infinity as opposed to 0. On the right here is just one more kind of fancy plot showing that you can also do 3D rendering of this thing by evaluating this function as a function of theta and phi. So that's the spin-weighted spheroidal harmonics. A couple of other packages. We have the Kerr geodesics package. So as I said, this one was used to produce that movie on the first slide. Here's an example, a couple of lines of how you might do that. You need to specify the orbit, so how the spin of the black hole is 0.998. The semi-large rectum is 3, the eccentricity is 0.6, and it has an inclination of pi/4 relative to the equatorial plane. You generate an orbit, and then this orbit function can be used to evaluate the orbit along a parameterized geodesic, parameterized by lambda. And we can produce these sorts of nice plots very easily that way. So it's good for visualization, but it's also good for lots of more serious physics calculations. For example, say you want constants of motion, you want to know the orbital frequencies, you want to know about special orbits like the innermost stable circular orbit or the innermost stable spherical orbit, or there's a separatrix between bound and unbound orbits. And as I said, you can also get the orbit trajectory. Relatively recently, a couple of years ago, there was also a sub-package added for doing parallel transport along those geodesics. That's GD6. A quick example of the Teukolsky package. So this finds solutions to the Teukolsky equation. And again, it's trying to present it in a fairly user-friendly way. So when you want to solve, for example, say you have a point particle in orbit around a Kerr black hole, you want to work out what the energy flux is from that point particle. Well, what you can do is you can load the package at the start. You can set up the orbit that the point particle is on using the Kerr GD6 functionality. You can then use the Teukolsky package to work out the L equals 2, M equals 2 solution to the Teukolsky equation for a point particle along that orbit. And this gives you this Teukolsky mode object, which you can then, for example, query the fluxes from that. And you get the energy flux and the angular momentum flux through infinity and through the horizon in basically 3 lines. And this is the sort of thing in the past where you would have had to write your own code and debug it and all the rest. Now it really is very simple to use. As I said here, fully generic orbits are coming soon. That's one of the things we're maybe hoping to improve on this summer. So I've shown you a couple of the Mathematica packages now. They're certainly very useful for sort of interactive and analysis type problems, but they're also very useful for doing kind of serious science calculations. And a very nice example was back in the end of 2019, so about two or so years ago. I worked with a number of collaborators on a calculation where we were trying to add spin to the small black hole. So we were trying to compute the flux for a spinning body on a circular orbit in Schwarzschild. When we started this calculation, it was before the toolkit was really robust enough to be used. So we spent a lot of time, many long hours spent writing debugging code, figuring things out, and getting it to work. It was very satisfying at the end that we went back, and in one afternoon, we were able to reproduce all of the results more accurately using the toolkit. That's really the goal, that just make doing science easier. So those are the Mathematica components. I could maybe just briefly mention some of the others that we have. So on the C++ Fortran side, we have the EMRI suite for doing kind of approximate waveforms for EMRIs. We have the Gremlin code contributed by Scott Hughes. This is a very efficient Teukolsky solver. We have a code for doing inspirals, fast self-force inspirals. And we also have this time domain self-force 1D code. This you might recognize from the Einstein toolkit as well as from the Black Hole Perturbation Toolkit. It actually lives in both, which is a nice connection we have between the two communities. We also have a number of Python or Sage math packages. So there's an EMRISurrogate package. So this is a reduced order model for extreme mass ratio inspirals. There's a Kerr GD6 gravitational wave calculator. There's a quasi-normal mode package contributed by Leo Stein. It works very well, very robust. And one of the most recent ones is this fast self-force inspirals. Niels will actually give you a bit of a flavor for this in his tutorial later. So just to pick one of these, I'm not going into too much detail. If we take the EMRISurrogate, this was one that we really like to highlight because it has a couple of nice features. It was quite recent in the end of 2019. What we were really happy about was that the paper both used the toolkit, so they used the toolkit to do part of their calculation that they described in the paper, but then they also extended it and they contributed their extensions back in. So it really was a win-win for everybody in that situation. This code produces a surrogate model for EMRI waveforms. It's implemented in Python. There's lots of nice examples and tutorials and data stored on Zenodo, and you can produce these sorts of waveforms. Okay, just in the last little while, I might just touch on the other side of things, the data. So we've talked about the codes. We also have try and collate as much data as we can, gathering them from any papers that are published. So there are a number of repositories on GitHub that have these. There are ones to do with numerical values of things for circular orbits in particular for now. There are post-Newtonian series collected together. There are these regularization parameters that I talked about as well that are useful in self-force calculations. And there are also a number of examples on how to actually use the toolkit to do interesting calculations. So far, many of these data sets are small enough that we're actually storing them directly in repositories on GitHub. although that may change if they get too big. So to pick out one of these, let's just have a look at the PostNewtonianSelfForce package. That's a collection of machine readable post-Newtonian expressions, but there's also a Mathematica interface to them. And this is, for example, how you might use that interface. You would load the package. You would then specify that I want the gravitational wave flux for the L equals 2, M equals 2 mode. And I don't want any spin, so a Schwarzschild case, and it'll load this object. You can then ask it for this post-Newtonian series. I've just printed the first 8 orders here. Some of them have quite high order, for example, up to 22 post-Newtonian order. So you just change this 8 to 22, and you get a much longer expression. So far, this has been stored in just in Git repositories because it's relatively lightweight, although it takes a long time to compute these things. They're just rational numbers in the end. When things are starting to get bigger, we need to rely on more robust storage, or certainly robust at holding large things. So we start out, for example, with Google Drive, but quite quickly, once there's a paper, for example, the surrogate paper, they also published their data set, their surrogate model on Zenodo. And this was large enough, it was several gigabytes that it would only be reasonable to store it in this sort of form, where it has it, and then also in the way where it has a DOI and the rest. Okay, so that's kind of a summary of the toolkit. I'd like to maybe just give you also a kind of a picture of how development works as part of the Black Hole Perturbation Toolkit. So in terms of hosting, everything is hosted on GitHub, including the website. We use all of the built-in issue trackers that are provided by GitHub. We don't provide our own. We do have our own independent continuous integration testing server, which runs Jenkins, much similar to what the Einstein Toolkit has used or up until recently. And we've also been able to integrate that Jenkins with GitHub. So in the bottom left here, you see the Jenkins web interface. And you can see a number of packages. And you can see the Reggie Wheeler package was having problems this day. Her GD6 maybe had just been fixed. And the other ones are in good health. And it tells you how many are passing the various unit tests that we have. On the right here, you can see the GitHub interface on the web. And the thing I want you to draw your attention to is just this little tick here. It seems very innocuous, but that actually represents the fact that after this pull request was opened, Jenkins was fired up, run the unit tests for that particular package, reported back, and said, yes, all the unit tests still passed. You can merge this pull request without worrying about breaking something in the process. And this one is a public-facing interface. It's just on the GitHub website. The Jenkins one, we have to keep password protected just because Jenkins is less secure as a system and it's not something you want to open to the web. But the GitHub one really provides the important information about whether your tests are failing or passing. So this is how development happens. What about if you want to get involved, if someone's kind of taking an interest in this presentation and wants to get more involved? Well, first thing you can do is download and use the code. Have a go. So here is just a screenshot from one of the web pages, the one for the Teukolsky package. You can see it describes what the package does. It solves this equation here. And up in the top right, there's a big red button here saying install this package. So go to the page for the Teukolsky package and click this button, and it'll tell you what to do. Once you've downloaded the package and started using it, you might discover there's a problem, or perhaps there's something that you would like it to do that it doesn't yet. So the best thing to do is go to the issue tracker on GitHub, click on the issues, and either report the bug, request an enhancement, or even better, suggest an improvement and provide code. If you want to do the latter, the best thing to do is to submit a pull request, push the code to GitHub yourself, go submit a pull request, and we will try to merge it in. And these pull requests could be anything, could be a trivial bug fix or documentation fix, could be new unit tests, they're always very useful, or it could be brand new functionality. Anything
10 minutes.
So that's the first way you can get involved, is download, use, and give us feedback on the code. Another way you can get involved if you want to learn more is to participate in some of our workshops. So our first workshop, the first public one, was due to be in Prague in March 2020. Unfortunately, that one had to be shut down as an in-person experience, but it went online, and we did save the recordings from that, and they're available on YouTube on the Black Hole Perturbation Toolkit channel. There was a second workshop, which again was online. It was due to be part of the ICERM meeting in Brown on advances in computational relativity. Again, that one had to be online in the end because of travel restrictions, but the talks and tutorials from that are all recorded, as are the tutorial materials, the notebooks and things like that. They're all available online on the ICERM website. And these workshops offer a couple of things. One is training for new users from the toolkit, and also an opportunity for developers to come together. As of right now, we don't have any training workshops announced. So the best thing to do is to go back and look at these recordings. But we are planning a developers workshop in the summer, where we're really hoping to progress a lot on things that need to be improved in the toolkit. That's one way to get involved. Another way is that we are preparing a paper. We have a draft, and it's fairly well advanced. We're aiming to have it out soon. This paper will describe the various components of the toolkit as they currently stand, and anyone who has contributed to the toolkit in a meaningful way will be invited to be a co-author. So that's another motivation for people to get involved and contribute back to the toolkit. Another thing you can do to help us out is, if you download the toolkit and find it useful, you can acknowledge it. It does help us significantly in terms of when we try to get funding for running things. Being able to say that people are using it and how many people are using it is very valuable. So until the paper is published, the best thing you can do is, there is a citation guideline on the website. If you go there, it will point you to this one sentence: "This work makes use of the Black Hole Perturbation Toolkit." And this is how we keep track of papers that use the toolkit. You can a search on archive or on the web will pick up all the papers, and we keep track of things that way. And if you want, you can also download this BibTeX entry that you can use. Okay. So in terms of our goals for the future, well, we have a few near-term things. One, we want to write a paper describing it. Two, we want to continue to communicate and bring people into the community. We would like to run some more workshops. Now that being back in person is a thing again, it would be great to have an in-person workshop. We want to do some further work on standardizing data formats. It's all well and good to have data, but you really need to have it in a standardized form where it's easy to understand and easy for someone else to pick up and use. And another thing we kind of need to formalize a bit more is how toolkit contributions have been fed back to us. So up until now, it's been a fairly ad hoc process where people have talked to some of the core developers and it's gone along from there. But I think we're at the point now where we're large enough that we need to formalize things a bit more. In the longer term, we'd like to see that community keep growing. We'd like to encourage other researchers to get involved. And in particular, there's what's called the second order self-force problem. Is a really big challenge that we face over the next 10 years as we're looking towards LISA. That's completing that H2 that I mentioned before near the start. That's something where we really need manpower in helping us with. We'd like to have kind of complete the code that we have already in terms of go beyond circular orbits and simplifications that we have in there so far. And ultimately, really what we want is to have a set of tools that are usable for LISA to make really accurate waveforms for doing the analysis that LISA wants to do. So I think I'm nearly out of time now. I want to maybe finish up with just 2 slides pointing you to a couple of instructions. These are ahead of the tutorial later this afternoon by Niels Warburton. So he'll show you some of the Mathematica packages, and they're pretty easy to install. If you go to this link here, bhptoolkit.org/Mathematica-install, you'll get instructions very similar to the ones here. It's essentially just a couple of lines. You add our server, our package server, packlet server to tell Mathematica to know about it. You then download a list of packages that are available, and then you can use this packlet install command in Mathematica to install the various packages in the toolkit. And if there's ever an update, a new version is released, you can just rerun steps 2 and 3. So it's a very simple process. If you have Mathematica to hand, I'd recommend having a go at this before this afternoon, so you could follow along with Niels. My last slide is also pointing you to a second set of packages, or a second package called fast EMRI waveforms. So Niels will start with some Mathematica demonstrations, but we'll finish up showing you how to produce a full waveform for an EMRI very rapidly on your own computer. These instructions are gathered from the README file for the repository, which you can get on github.com/Black Hole Perturbation Toolkit /fast EMRI waveforms. So if you go here, look at the README file, as you scroll down the page, you'll get these instructions. Essentially, what you need is Anaconda. Is the easiest way to do this. If you have that installed, that provides Python and all the Python packages that we would need. You create a new environment, including all the dependencies that are required. You clone the fast EMRI waveforms repository. You run the install script, and then in Python, you import the fast EMRI waveforms package. So I think I'll leave it at that and leave you with this screen here. And if there are any questions or comments, happy to answer them.
Great, thank you, Barry. All right, let's see, opening up the floor to any questions. Roland, yeah.
So, hi Barry, you mentioned LISA a little bit. So I'm wondering if there's any closer interaction with the LISA working groups and also in any software and data formats that they will try to develop for EMRI waveforms in particular.
Yes, so Niels Warburton, who'll be talking later, is one of the main developers of this fast EMRI waveforms package. And he is also a member of the LISA work package on EMRIs. I'm also a member of that work package. And so I think one of the ideas is these sorts of tools will eventually evolve into some of the LISA tools that are used for EMRIs. That's at least our goal. So in particular, fast EMRI waveforms is designed to be fast enough for data analysis purposes. So it's designed to fold in as much information from big, hard, long self-force calculations into a very efficient code that runs on GPUs and will be used hopefully by the LISA analysis.
Cool. Any other questions? All right, just a quick one. So I know that a number of the codes in the Black Hole Perturbation Toolkit are Python based. Are any of them pip installable?
Good question. So I don't know about the fast EMRI waveforms. The instructions at the moment are to use Conda and then just clone the repository yourself. I think the GW package is pip installable. So if we go back, let's see the Python ones here. I think the EMRISurrogate is, and I think this one is. Certainly the QNM package is, can just be installed with pip. Yeah, and this one, I'm not sure if it's quite made it in yet.
Very nice, thank you. Yeah. All right, anything else? Any other questions?
30 seconds.
Thank you, you fit nice in your